Hello, I'm Rebekah Wilson, CEO and co-founder of Source Elements. The last year has been an immense one for the field of network music performance. It's been a great opportunity for me to present here an overview of the current status of the tools for this field. In the last 15 years, I've dedicated the larger part of my life to developing tools and workflows for remote audio and video collaboration, and at the same time, I've been active as a composer and music technologist. A few years I went back to university to do my graduate degree in the field of network music performance in Wellington, New Zealand, and I currently teach network music at the Royal Conservatory at The Hague in the Netherlands. What I'll be presenting here today is an overview as it stands of the tools and services that have been created and maintained by the music community. Tools that allow us to play music together while we're apart. After a brief introduction of the topic, we'll look at what the specific technical considerations are shared by each offering. What I'll be presenting here today is an overview as it stands of the tools and services that have been created and maintained by the music community. Tools that allow us to play music together while we're apart. And after a brief introduction of the topic, we'll look at the specific technical considerations that are shared by each offering. I'll discuss in most detail the options for audio, but also touch on videos as is important for performance. I'll also introduce the WebRTC project and how you can build your own applications for network music performance. Network music means that we perform together on the global stage. When we play remotely, our listening is distributed across cities, countries, and continents, and one day across even greater distances of planets, moons, and satellites. And with network music, we can perform without boundaries, without borders, across borders. We're not limited by passports or visas or travel funds or physical mobility or our health. We're not limited by viruses. As musicians and audiences, we become multi-located, we become multi-authorial, we have multiple audiences and experiences, and each on each side are as valid as the other. We're distanced from each other, and yet when we create together, we move in time together, we experience the same feeling of being together that music makes us feel, regardless of where we are. There's another discussion at this conference that defines network music performance with Miriam Iworth, so I'll be very brief with the definition and encourage you to look up that discussion. Essentially, network music can be defined as performing music together in real time over the internet, where participants are separated by distance, whether that's another city, another country, and eventually celestial bodies, and where our response to each other is sufficiently musical. And by that, I mean that we have sufficiently low latency and high enough audio quality that we can make responsive musical decisions, or we learn how to make responsive musical decisions regardless of latency. This definition of network music allows us to assert the physical conditions that are ultimately distinct as to how we traditionally make music together. Our sound is digitally encoded and transmitted, and what we want to be able to do is accurately transmit and reproduce our sound, that we are inhabiting distinct physical spaces. We want that experience to be transmitted. And these conditions create 4 primary constraints of latency, acoustic feedback, digital mediation, and remote performance behavior changes. First, latency is the unavoidable properties of physics. Second, acoustic feedback is the result of working with microphones and loudspeakers. And third, by digital mediation, I mean that our signals are digitized, encoded, and decoded, which gives us opportunities we otherwise don't have when working together in a single acoustic space. And fourth, by remote performance behavior, I mean how we behave and accommodate for each other when working at a distance. These constraints mean that we're really dealing with something quite new when we play together. For musicians, not being in the same room is very disruptive. Eye contact is something we really miss when we don't have it. Yet fortunately, we as humans excel at communication, and we're constantly seeking ways to accommodate for this. We use video, we use cues in the music or in the software. Some might work with a conductor, some might write a digital score that is shared across locations. And ultimately, performance behavior is one of those things that we can control. We manage culture change continuously. We're really good at this as humans. And audio echoes, feedback, lower audio quality. These are created by needing to use microphones, headphones, speakers, audio compression. Instead of enjoying full bandwidth audio we get in real life, we have to adapt to these limitations, and this is where our technical prowess can really shine. For this, there are increasingly sophisticated tools available. Network instability, on the other hand, that's an issue only we can solve together as global partners. Many of us have excellent internet access at our fingertips, and some of us less so. In a future world of 5G, affordable, low latency satellite, and true global fiber optic internet does offer hope for a worldwide future where students, musicians, schools, ensembles, orchestras, choirs, we can all play together. And as we'll see in the next section, many tools are actively in development. They're becoming increasingly mature and easy to use. A lot of the anxiety that we get as musicians arises not only from the technical instability of the internet or new software, but from us, or as musicians, not knowing how to use it, from not having the training or the tools having more complexity than is necessary for all use cases. So as we design more intuitive tools, and as we play together with those tools, we learn and practice how to improve them and how to push them further to keep up with our developing creative processes. For many years, the open source and academic communities have been developing projects, such as I'll show you soon, and born from both a research project and a sheer love of the genre. The pandemic has put these projects front of center, and quickly many improvements were seen and continue usability and innovations. Regular conferencing tools don't work. Not for music performance. The entire purpose of audio conferences is for speech intelligibility. Speech intelligibility, not music. That one got me. Commercial conference services use echo cancellation so participants don't need headphones. And for music, this means that the signal will have really strange artifacts and doesn't reproduce the full frequency range. And commercial applications also provide low sample rate support. We really want at least 44.1 kilohertz and 16-bit, if not 24, 32-bit, 64, 64 when we come. And these conference tools also, they're usually mono to save bandwidth. For example, they might offer stereo with an option for echo cancellation, but Zoom, for example, still only has a sample rate of 32 kilohertz, most likely to save on bandwidth and server processing costs. Further, it really only allows input from stereo audio channels, which adds complexity for routing. Narrowband audio, which results in often quite a harsh codec compression, further means that music signal fidelity is lost. And where commercial and free software differ the most, it's really expensive to run servers because of the bandwidth and the CPU costs. And this is really needed to get around the issue of ports and firewalls and bandwidth usage. Commercial applications tend to have quite high latency, as they will use oversubscribed or low performance servers to accommodate for the cost. So while free server software works best when you can run your own servers, that's a great benefit for performance and latency. There is some investment involved, but you'll certainly see the results. To get data from one location to another, network traffic must flow between private networks. Sending traffic between us is most easily done using a relay go-between, which acts as a pass-through. However, this adds latency and server costs. It's generally recommended from this while working at home that you learn how to open ports in your router, though of course it depends on the use case. The lowest latency solutions are certainly the more technical, the more demanding. There may be a barrier to entry, and in some cases it may not be possible, especially inside institutional networks where there are secure firewalls or you don't have access to routers. And for longer distances, getting network latency down a few more milliseconds may not be really beneficial if participants are already far away from each other. So it's a consideration to take depending on your geography and performance conditions. Latency is an important topic for network music. We've been performing together for eons in relatively small spaces and distances. We've adapted to experience physical latencies that exist, latency for air transmission across a room. We have neural processing, cognitive processing, biological processing. Music doesn't arrive at us instantly, but we've adapted and our brains have evolved to experience this as no latency, when in actual fact, there's always these latencies around us. So if we're experiencing a little bit more latency, this to us is very new, but we can certainly learn to adapt. Because over long distances, latency is unavoidable. Latency is not going away. We can only approach the speed of light. As you can see in this animation, the speed of light, once you get to a large enough scale, really introduces latency beyond what musicians are accustomed to. And once we get to Mars, if we do get to Mars, well, we really need to consider what it means to make music together. There's latency between even London and New York. There might be mere milliseconds by the speed of light, but it's an average of around 70 milliseconds through the internet, the average internet, once you packetize and route data through several machines. And that's a lot more than our ears expect when we want to play music together. So we need to adapt culturally until at least we've broken the speed of light or invented time travel. So with this technical overview in mind, I'll now review the most popular options available at present from the perspective of how they meet the essential requirements that we know are necessary for music performance. We need low to no compression, no echo cancellation, wideband, high bit depth and high sample rate audio, and low latency, at least as low as possible given the constraints. So fortunately, we have these dedicated tools made exactly for what we need, and they didn't just show up last year. Certain technical milestones over the last 20 years has allowed network music to flourish to the stability we have today. The most important, of course, being broadband. What a marvel it's been that we've lived through a quarantine, and by and large, our internet services have been rock solid. That's no small feat, and we should recognize and celebrate that achievement. And all these tools have two ultimate goals: to connect users at the lowest possible latency and to transmit music with the highest possible fidelity. And all network music is somewhere on the spectrum between supporting small ensemble numbers with super low latency and maybe a bit more technical complexity due to firewalls and port forwarding, or alternatively more participants, a little bit higher latency with less technical complexity and some server costs. So everything in there is in a balance between those. We can also reduce, of course, the geographical distance between us. We could choose to perform with musicians who are closer. We could choose to travel a little bit closer where possible. But of course, this may not be practical. So another benefit too for not using compression, for those that do, is latency. So for wideband audio, Opus can add around 25 milliseconds of latency. Though uncompressed needs more bandwidth, so you're going to need, say, almost a meg compared to Opus, a sixth or an eighth of that for a decent stereo signal. So secondly, it's absolutely critical that we don't have echo cancellation. Echo cancellation creates very strange artifacts. I'm sure you've been on a phone call when a plane goes past and the voice gets interrupted. Echo cancellation does that to music. It's really, really bad. It just suppresses the frequencies. It's designed for voice intelligibility, and it actively works to suppress non-vocal signals that are not in the regular speech range. So in the following section, I will introduce a number of the popular projects in use today that have already been in use for quite some time and bring them with them a great stability and, more importantly, a great community. Each project meets the requirements that we need for network music performance, being high quality, full HD audio without echo cancellation, and as low latency as possible according to their design. Jacktrip was developed at Stanford by Juan Pablo Caceres and Chris Chafe. Since the early 2000s, it's been the most mature tool used around the globe for many countless projects. It doesn't use any compression, and it runs on a low-level process. So latency is extremely low. It's been very tested in many situations, and it's increasingly easy to use. Though time investment will be needed, there's a vibrant, busy community available to help. And the Jacktrip Foundation now provides official classes. There's also a great course online, Condens with Chris Chafe, which I highly recommend. So Jamulus was started in 2006, written by Volker Fischer and succeeding contributors. Jamulus utilizes a client-server-based topology, which has the benefit of not requiring port forwarding. And these clients are very easy to install, get up and running, even for people with limited technical ability. Each Jamulus client transmits compressed audio to a server elsewhere on the internet. And this mixes the decompressed audio stream on the server and retransmits a compressed mix to each client. So this method does mean that there's extra latency. The trade-off here really is convenience and the ability for many tens of participants. The travel must travel through a relay first, adding a little bit of extra delay. But because of the design, Jamulus supports large groups out of the box. There's been some really fantastic projects with choirs, as many as like 100 members, and setting up a server is very well documented, and the Jamulus community is very active. Developed by Dr. Alexander Karas since 2006, Soundjack is another great low latency desktop application with a browser interface that operates in both peer-to-peer or hub mode, similar to Jacktrip. And it also features experimental video support, so it's a great one to try if you want to work with video. And very easy installers for Linux, macOS, and Windows. And the interface design involves the application running on the desktop, and that connects to a browser, which is great because this allows developers to really quickly add new features to the interface. You only need to write the UI once, so it's a very clever idea and allows a lot of flexibility. And Sonobus is a new project that was developed only last year that has had immediate success as the interface is very intuitive and very powerful. While it cannot support large numbers of users as a strictly peer-to-peer architecture, for small groups it's very easy to use and implements some excellent latency detection and management techniques. Unlike more established tools, it doesn't have much of a community yet. However, the ease of use really makes up for it. But when musicians play in the same space, we use really rich visual cues. We may nod at each other when we're going to start. We may move our bodies to indicate that we're going to change the timing. And being able to see each other is how we work, how we stay in rhythm, how we change pace while we're also listening. However, over the internet, video takes more time to process than audio. There's a lot more data to take care of. The CPU requirements are a lot more heavy. So we can't really rely on video cues for exact timing. However, it's still comforting for us to see who we're playing with, or in what context we're playing, what the environment is, what time of day it is, especially when we're working across time zones. So unlike audio, even HD video, video really needs a huge amount of bandwidth. And for this reason, there's no free, really super low latency, easy to use, high quality services. Those just tend to have higher latency like Twitch or YouTube. And then of course they're ad supported and not really low latency enough for our purposes. So when latency is critical, you're going to need to look for a peer-to-peer technology. Although that will also require, of course, sufficient bandwidth. So, and we're also limited really in that context, only being able to send a small number of streams. For this reason, the free video services don't exist with this super low latency. However, when bandwidth is plentiful and you only need a point-to-point connection, one of the best is UltraGrid. It's easily an excellent choice. UltraGrid is a project from two Czech institutions, CESNet and Setola, since 2005. Another great mature project. And like Jacktrip, it has some technical learning to use it, but it does pay off in terms of quality. Latency and flexibility is fantastic. It can ingest directly from high quality cameras or HDMI converters, and then it can stream directly up to 8K directly to remote monitor screens, really saving a lot of CPU power from being able to need to screen share, for example, which is a very CPU intensive process and should be avoided. UltraGrid is capable of transmitting uncompressed or very low compressed video as well as audio. So it's excellent for color and accurate work as well, and is even employed in medical cinematography. And note that UltraGrid is really one-to-one only. For multi-user setups, you would need to duplicate the streams manually, and there's no server relay, so you would need port forwarding. This graph shows how much dedicated bandwidth you'll need for high definition video if you want to avoid frame dropouts or significant buffering. It's quite a lot, though these days with fiber in the home, it's definitely possible, though perhaps not for very long distances unless you have a dedicated connection on both sides. Lola is another notable project that empowers musicians to cooperate and work together seamlessly in real time across the globe, particularly with a focus on classical musicians rehearsing and conducting masterclasses between institutions. It was started by Massimo Paravel in 2007. It's shareware or free for non-profit use. This project provides software, however, it does have additional requirements. Lola is a state-of-the-art advanced system composed by the software and in combination with certain high-performance and specialized hardware and a high-capacity, reliable, error-free symmetric connection into network service such as Internet 2 or Geont that are found in the scientific and university institutions, for example. As all of the above three elements, the hardware and the high-end internet, are needed to use Lola, so usually out of the scope for first experiments with network music, but it does offer a truly magical experience when properly installed. So these two video applications are heavy lifters that require really special network setups and dedicated hardware. But what if we want to work from our phones or laptops or tablets? We accept it first of all. We're not going to get super low latency HK video. But we have all spent many of the last months on video chat, and we know we can have conversational chats on generic software in our browsers. So here we have WebRTC, which allows us to do that, along with audio over OSD, for example, WebSockets. There's various ways of doing that, and rolling your own is the best way to get to know network music performance technology. It will teach you about buffers and jitter, codecs, bandwidth, all the technical issues that the projects discuss here deal with in their own way. There's plenty of room still also for exploration. I think WebRTC is a great place to start. You can build applications really easily. It's an open source project. There's ever-growing support on various devices, levels of programming experience. You really only need to know JavaScript until you want to look at embedded devices. And every modern platform and browser is supported. So it's a really great start. And standard WebRTC applications that you'll find, Google Meet or others like this, are designed for communication. As I mentioned, they for voice intelligibility. And thus they'll use lower bitrate codecs, often mono, and they'll enable echo cancellation so that people don't have to be worried about wearing headphones. For music, we need to configure our settings correctly. So one great way of getting to know the settings for WebRTC is the Jitsi project. One of the most beloved open source WebRTC applications was started by Emil Evov all the way back in 2003 using pre-WebRTC technology. And they've since ported everything to take advantage of the modern capabilities. I particularly like Jitsi because it makes the application very configurable, and we can get a good sense of what generic WebRTC apps are doing that create the environments bad for music performance and teach us how we can use them for good performance. And I'll just break this down. We have P2P enabled, so it's peer-to-peer. We want this so the audio doesn't pass through the server where it would be mixed to mono in the regular Jitsi application. We want to disable audio processing. This is any other processing that may affect the audio quality. We definitely want to disable audio echo cancellation. And there's automatic gain control, which will lower your microphone gain if it, to try and keep a balance. And of course, the high pass filter, we want to turn that off as well. We can see from this list, and there are more, that all this audio processing goes into commercial apps to give a better voice experience. And this affects sound quality, this affects music quality. So this is really why you can see we need these dedicated tools for music purposes. You can also see the source code of how Jitsi works. It's a really great exercise. Just a great example of a WebRTC app that I think has done really, really well is LiveLab. You can get that at livelab.app, I think. And it features multi-camera video, desktop sharing, high-quality stereo audio. It's multi-participant. It's a really fantastic example of all the things you can do to make a great performance application. Given the limitations of the browser, which has many, it's certainly a little high latency than others and can be a little unstable in terms of buffering. It's a very good example of an implementation that works for many, many use cases. It's already configured the best settings for you, so it will sound fantastic out of the box. And as we saw with Jitsi, in order to use WebRTC for music performance, we need to make sure that we can configure it correctly. So for all the WebRTC applications, it's more or less the same. I've put some code examples here that if you do decide to dig into WebRTC to make a music app, these are the two areas you want to really modify for music quality audio. First, you disable the echo cancellation when setting up the media device and the get user media callback. And secondly, you want to override the session description protocol, or SDP, the payload. You need to enable stereo and full band compression. In this example, I've put in 500 kilobits, for example, but you can do lower. The Opus codec still sounds pretty good, even 128 kilobits a second. For a full description of these settings, there's a very excellent site, WebRTC Hacks, for their anatomy of the SDP. This is really a Bible for SDP analysis and manipulation. Those of you who are interested in WebRTC can find many guides online, and I cannot recommend highly enough that you attend the Web Audio Conference that's going to be held again this year in July remotely, so there's no barrier to entry. So embedded systems, can't forget those, just a Raspberry Pi, anything that runs a various Linux distro, certainly becoming more useful for network music performance. You can get really good low latency, especially something with ELK, a great new audio operating system for real-time performance. It's an example where you can get the best of software combined with the best of hardware in one and the same instrument. They also include support for VST, so you can integrate your ELK applications with your DAW, and Jack Virtual Studio from the Jacktrip Foundation, and Soundjack also have images for Raspberry Pi, I believe. And I look forward to seeing these come out on ELK OS as well. That will be really interesting. I hope someone's looking into that. You can also run pretty much any WebRTC application on embedded hardware also. So if you just do a web search for WebRTC embedded, you'll see many, many, many results. While there's always more that can be said on the topic, not only is it very meaningful right now to talk about network music performance, but there's a wealth of projects and examples going back the last 2 decades. And I hope this overview helps those of you who are interested to get started. There are many projects to choose from. They all have a particular focus and were designed to meet a particular need. Once you know what you're trying to achieve, it would simply be a matter of choosing the right platform. I recommend playing around with them all. You'll find the one that works for you. For example, if you want lowest latency possible, you would want to use an embedded device such as ELK Audio or Jack Audio, Jacktrip. Is also a great example, if you don't mind, to do the extra network configuration with Soundjack also. If you're looking for something a little bit easier to get started, Sonobus is super great for that, and Soundjack also in hub mode. So unless you have firewall restrictions, I would take a look at those for sure. And for video, most of you probably are happy with the synchronization being off a little bit, so you could just use any video conferencing platform and mute the audio on that, for example, and then use and the other audio application that you're using for the sound. The information presented here was derived from research collected at the Network Music Performance Library that is available at the Source Elements Academy with free access. So you can find links there to all of these projects discussed today, plus a transcript of this conversation, all the links, and there's a lot of events and conferences, classes, courses, and learning opportunities. So thank you so much for watching. I hope this information has been helpful.